So I'm making another video. I have the technology, might as well use it, right? Just sorry. These are all interesting subjects, so I might as well. Alright, so Steve Beck says, to his credit, he calls Dissonant Science Guy on his no existence to charge kind of crap, so that's good. That idiot who said protons and neutrons are made of smaller particles was me. Well, I don't have any problem with the neutron one for certain. I mean, obviously, I think neutrons are a proton and an electron. And, but the fact that protons may be made out of smaller protons, I'm not saying it can't possibly be. I just tend to doubt it. I just tend to point out that I don't think we really know the size of anything. Or the mass of anything very well, because the way we have to measure them are very, very crude, and we might miss a lot in attempting these measurements. And maybe I'll illustrate that. Yes, since I can, I will. So to the drawing tablet, the paper. Yeah, I find a place to put my mouse. All right, so let's say you want to see, you know, how much an electron weighed. I mean, you could kind of say, okay, I'm going to blow energy at it and see if I can compensate for gravity. But what if, when you're blowing energy, you're also blowing some energy this way, and we're blowing some energy this way, and some energy this way, and some energy this way. So, in a sense, most of your energy isn't blowing on the electron. Blowing on this other stuff. So you say it took 5 watts to maintain the electron in that position for, you know, 10 minutes or something, and you come up with some equation that says, well, this is how much the electron must weigh. Well, then obviously your weight won't be exactly accurate because you've missed all this extra energy. And you know, a question that I'm stuck wondering about is with polarization film, right? So, you know, you have this idea of, you have this piece of film, you shoot light through it, and 50% of the light doesn't get through. Where does it go? I mean, does it make this thing hot? As I think, does the light itself continue to go through? It's just no longer in the form of visible photons, or it's no longer in the spectrum of continuous photons. So in a sense, the fact is, for any photon to affect an electron, it has to be a certain length of ray. And if it doesn't have enough of that ray element to it, that is, the photon isn't sufficiently substantial enough in terms of the number of bullets in it, then an electron is going to just not care. It's going to be like kind of a gravity thing. It'll absorb a little bit of gravitational momentum, that is, a little bit of movement, but that's what it's going to do. And as demonstrated by this gravitational argument, this is a huge amount of energy relative to what a photon can do. So, you know, obviously gravity is a substantially strong force relative to photons. And we need a lot of photons to imitate gravity, to create as much energy. So obviously our ability to measure the gravitational effect, if we can't see it as a light effect, if we have to see it by seeing it as motion. So we're not going to see it as electricity or some electron wibble. We're going to see it as an electron's motion in the sea of, you know, an apple is to an atom as the earth is to an apple. I mean, the electron is so diluted in its capacity to spread its momentum across that entire substance for us to measure it as gravity. So there'd be no way for us to perceive light unless it does its frequency thing. It does its special little thing where it causes the electron to do a special thing. And we know that's very specifically frequency bias. Some substances are transparent to ultraviolet light and and opaque to visible light. Lots of substances. Glass, opaque to ultraviolet and mostly. Opaque to infrared. Yeah, that's mostly, partially. Well, anyway, it's one of them. But I mean, we know there's the mica, all kinds of stuff that is perfectly transparent to ultraviolet, but you can't get visible light to save your life through it. So we know it's all very frequency dependent. And so if the frequency is broken, the energy from our ability to see it is broken. Alright, so that's sort of a preface for a more complex argument that I will make regarding the specifics of his point. Okay, and I was that person. Not what I'm looking for. The other computer's calling. Oh, no, sorry. Yeah, I can pause, so that'd be so cool. I have to do a little auction real quick. I should be back. Sure, sorry, a little bit time consuming until I'm more confident in this software working. Anyway, lost the auction. $2. I'm spending $2. Anyway, Particles was me, and I was that person that he ragged on for charge. Yeah, so look, I don't, No, I am sort of saying some things. I'm just saying, okay, you people can love this whole idea of atom smashing, but on its face it does sound like the hard way to figure out how something works is to smash it with a hammer. Like, you're going to break the circuit boards and break all the stuff that would be significant in a way, right? You're not going to really get to how it was put together. You're going to get how it falls apart, which isn't the same as how it was put together. Anyway, quark theory, I know there was a whole theory, has not a small number of problems. Yeah, well, one of the problems is they don't see quarks. So that's one of the problems. They don't leave trails behind. There's no hard evidence for their existence. It's this residual argument, right? It's that they have an event, they have a calculation about how much energy should be in the event, and then when they see an extra amount of energy come out, in the sense they're able to collect something extra, like some infrared or some other kind of radiation they can detect, like some ultraviolet or some X-rays pop out, well, they have to account for why that happened. And that's what most of this is based on, is that they're just conjecturing about what is the mechanism that allows for that result. So what they see is something collides with something, and then they see its neighbor over here break into pieces. So they know they hit something here, right? And then they see a residual explosion over here, and they're saying, well, it must be a piece of this collision that crashed over there. And they make an approximation about how much energy it must have been. But they have no idea what form the energy could have been in. And that's where I would argue that, well, the form could have been just a row of X-rays. A powerful X-ray emission could have caused the event. You don't need to invent a whole new quark to do the job. Anyway, but CERN and LHC and some other particle colliders smash protons into smaller particles. Well, I don't know about smashing big things into small things. I'm not too sure about that. But regardless, they smash a lot of stuff into a lot of stuff. So that's a key to this thing too. It's not like they send one proton through and smash it at something. It's a bunch of protons into a bunch of protons. But anyway, it isn't just an electron and a proton. Well, you say so. So again, that's certainly all that's in the damn machine to start with. What they get as a byproduct, again, is, you're going to argue to me that these are real elemental bits and they don't last. They have no durability. They can't survive outside of the womb. It sort of implies to me that they're not really elemental. But anyway, the proton is more massive than the electron. Right, and that's by measuring in an environment that's always going to have some kind of charge in it. So there's no way you can create any kind of vessel or any kind of mechanism to measure any of this stuff that's outside of the strength of charge. Charge is really significant on the atomic level and quite durable in some respects in terms of the inverse square law. May not apply in some circumstances. Counting on how small these things are, it's almost like everything they're attached to is an infinite plane. Yeah, I mean, an inch of space is like an infinite plane to an electron, right? I mean, realistically. All right, an electron by far, more massive than an electron by far. Yeah, by 1,863 or whatever the number is. Yeah, so yeah, it's bigger. I'm not saying it's not bigger. I'm not saying it's not more massive by how we measure mass. But I'm just saying, frankly, that might not have anything to do with it. In the sense that, what if the electron has twice as much volume? Like the planets, there's hard ones and soft ones. Well, if the electron has twice as much volume, or 10 times as much, or 100 times as much, or 1,000 times as much volume, the electron's going to do a lot more collecting. And I'd argue that the truth has got to be somewhere around there, because clearly stuff hits electrons really easy, and it doesn't hit protons too easy at all. So it seems to me that there's got to be a relationship that somehow justifies that fact. I mean, even if you cram the protons in a nucleus, I'm just saying, if you just go by a rational, doing some kind of pi math, you can figure out that yes, okay, if you're in a little group, you're gonna limit your surface area, pretty substantially, but it's not that substantial in the sense that it's not so big a difference to justify the huge difference between the likelihood of hitting an electron and the likelihood of hitting a proton. So, but these are all open questions, right? I'm not saying they're not worth discussing. I just don't know if they really play a role in any of this, because you have to contrive the role. You have to contrive a role for the quarks. You can't just say, oh, we already have a function for them. We had this unexplained thing. Well, now the quark explains it. It doesn't explain magnetism. It doesn't explain gravity. It doesn't explain anything important. So why do we need it? Would be my first, dig or shot. What is it? What good is it? What's it good for? I don't think it's good for anything. Dead giveaway, the protons are not elementary particles. Well, I don't know if it's a dead giveaway. Like I said, it just necessarily doesn't mean much, in my opinion. The universe doesn't have to obey some kind of symmetry rules in its creation of particles. Clearly, it did create symmetry in the end result, which is the amount of charge that holds the atom together. So clearly, you could argue that they're bigger, and the only way atoms would work is if they were more massive and they had some ability to you're still stuck with the fact that they still have what appears to be as an equal amount of charge. So I don't know. I'm just saying that you can't be too sure of your measurement, right? You think you can be? Well, I'm going to argue that I don't think you can, because you really can't. You can't really tell how much of your energy is actually affecting the thing you're aiming at. Because we know that it's hard to aim these little subatomic photon-y things at anything. It's hard to assure that every one of them hit the thing you're aiming at. So how can you go based on how much energy I put in, it's going to tell me how much energy I actually hit the thing with. Because we know it's not that easy to hit. Alright, your model is for the most part on the right track, but just the electron and the proton, question mark? I'm just saying for every phenomenon that seems significant, the fact that the electrons are a certain distance from the protons, the fact that the electrons are a certain distance from each other, the idea of the attraction, the repulsion, all you need is the electron, the protons, and the photons. You don't need anything else. The force is the stuff moving the speed of light. That's easy. The electrons and protons are creating the material conduit, the thing the force acts on. So two forces can't affect each other if they do this, but if they hit the conduit, then they can affect each other. They can create motion in one direction, then motion in the other direction. They can transfer their energy. Okay, but the possibility of a proton being a composite particle made of smaller particles with similar size to an electron is there. Well, then you're getting into this positron crap, which, I'm not saying it's not possible that positrons are part of what a proton is, but that's not what they say they are. They're saying they're an anti-electron. So, where does that go? I don't think that goes anywhere healthy. It is the particle's proton. It is the particle's protons. See, that's really getting into trouble. The particle has protons. Atoms obviously aren't particles. I mean, the only thing that should be called a particle is something elemental, right? Or almost elemental, or close enough to elemental. Like, I think it's okay to call a proton a particle, because from every appearance it's pretty elemental in the fact that they don't just turn into anything easy. They spend an awful long time just being a proton, and then we show up and say, we have done something to them. But do we really know we really did? It is the, I'm just sorry, I don't think we really do know that. Particles, proton, are made of that, let's see, it is the particles protons that are made of that is open for revision. I don't know if that sentence was great, but okay. This color charge, I mean, that's another getting into this whole bullshit of, you know, spin and, you know, using all these fake words to describe real things. I don't really like very much. So obviously in my theory I have used color just to distinguish between positive and negative. I mean, you have to use some kind of distinguishing element, but I just don't think these elements are very close to the truth. They're not very good metaphors or analogies or labels or synonyms. This color charge, flavors, and gluon stuff, to my knowledge, has little or no evidence. Yeah, well, I'm just saying that unfortunately, the evidence of quarks is also pretty, you know, it's like I said, I'm doubting positrons merely, and they have trails, they have a track of those, and I'm still going to make the argument that you don't know really, because you're basing it on a mass velocity equation, and you're saying you know exactly how many protons are going to get through a material and exactly what kind of condition and exactly what kind of speed it was going when it got there and all this kind of crap, and I don't think they can do all that. The positron does exist. Yeah, whatever. You know, I'm saying I don't know if you know what it is, though. Let's agree that something exists. But whether or not it's a low velocity proton or whether it's something else is open to debate, in my opinion. I mean, it also has the same charge as a proton, right? I mean, let's get realistic, right? Proton and electron have the same charge, you know, same opposite charge. So positron doesn't have a different charge than a regular proton. So how does that make sense? I mean, how do you combine them into closer proximity and in no way enhance charge? I mean, wouldn't the proton's charge be realized as a little stronger because of the fact that there's three of them consolidated? Not only the positron has been used in experiments, I would argue that I have absolutely I've seen no hard evidence that they have any such thing that ever creates a reliable positron. You can say it happens, but I'm saying that all of these positron emission, all the things they label that, are based on assumptions about what they put in, what it turns into, and then what it would get as a byproduct. So the turning into part happens inside the human body with a positron emission bullshit. It doesn't have anything to do with what they shoot or what they get back. They shoot what are you know, atomic particles, radiation, and they get back radiation. There's no positrons involved. All right, except for their theory about what happens inside the human body, what happens inside the atoms. So, again, I'd say that's not hard evidence of something's existence when they have to tell me that it happened, just as they tell me about the quark doing something. They tell me that the quark is what shot from this one little explosion and it jumped over to here. They say a quark did that. I say a lot of shit could have done that. It is also used in the medical field. Well, again, it's not used, so go ahead and research it. But I looked it up. I read the papers, and there's no positrons involved except for as a catalyst for the interaction. So the interaction, they do step A, shoot radiation in. Well, first they put radiation in the person's body, so they have radioactive isotopes floating around in their bloodstream. And then they hit them, you know, with radiation to activate them, cause them to decay. And then they have an explanation for how that decay takes place, and then it creates these byproducts based on how many carbon atoms it hits, or how many, whatever, hemoglobin molecules, or whatever the thing would be. And that the positrons are doing this stuff in between, causing the new radiation to be emitted that they detect on their detectors. So, again, there is no actual positron in the experiment that you get to see. It's all they're just theorizing about its existence. So they could call it quark emission, because for all we know, quarks did it. Anyway, known as positron emission tomography. Yeah, well, whatever it's known as, I would argue it's a misnomer. Okay, they haven't accurately, fairly, rightly It's like blaming Einstein for gravitational waves, right? I mean, it's just not right to say they're Einstein waves or something, because he clearly wouldn't want his name put on that crap. So this other guy says, without quantum tunneling, SSD hard drives wouldn't work. What a pile of shit. Just another Piroism. Prove that or shut up. Okay, so show me the documentation that demonstrates, first, that you ever can see a tunnel happen, and second, that there's any theory that says you couldn't have an SSD drive unless there was some sort of bizarre tunneling thing happening, which is just a pile of crap. Alright, do I need to say more? Maybe this is to keep it short and sweet, just this narrow subject. So yeah, I'd just like to go back to the drawing for a minute, just to emphasize that there's lots of experiments where we know a certain amount of energy is supposed to go in, and there's no experiments where they actually try to detect the energy out. So yeah, I could also argue that the radar experiment, for example, you know, they just say, oh, it's an interference pattern, but wouldn't it be interesting to know that can you actually detect a twofold increase, not in an audio signal, but in the actual radiation hitting a place at that location, and demonstrate that, you know, somehow the radiation that was going one place has been moved to another place. Is there any, you know, and there's been no experiments demonstrating these things, and so clearly you can waste a lot of energy in experiments, and you didn't know you wasted it, because it's not going to create some kind of obvious heat. And it's not going to, you know, it's not going to be detected by creating sparks or electricity. And the only way you could detect it would be measuring the gravity of some vessel that weighs 500 pounds. So you're going to shoot a laser light at something that weighs 500 pounds and expect to measure how much it moved because of the gravitational impact of the light, you know, the momentum impact. Well, obviously that would be impossible. So our least measurable, you know, even though this seems like, oh, look how measurable this is. Right, we're not measuring this to any kind of level of precision that we get to measure photons. You know, we can detect one little tiny ray of photons. We can't detect one little ray of gravity, because we have to have it hit something big enough for us to see. Now, if we could make little things and make the gravity hit the little things, that would be fine. But obviously, we can't see the little things, so we can't see how much they move. We can't see what the impact is. So you have to create a very complex sensor to be able to collect raw energy, because energy can be in lots of forms. The pressure can be in lots of forms. It can be in lots of manifestations that are not necessarily easy to detect, as is pointed out with just a simple jamming experiment. You know, you can not see something, right? You can have two radio stations blaring at you, and you can tune neither one of them in. Lots of energy, but absolutely no impact, no ability to detect, no ability to know it's there. And that's the truth with gravity. You know, you can be in between two highly gravitational bodies, and you can just be sitting there saying, I don't feel anything. I don't notice anything, because the pressure is balanced. So, but those are, you know, understanding, you know, this whole thermodynamic equation in a complete manner. I mean, that's really what's missing, and I'd say it's even missing for the LHC. So they pump in a ton of energy to move these protons, and so there's a stream of energy that's going with the protons that are moving. Voltage, okay, it's actual voltage. I mean, it's like a lightning bolt they're pushing these protons with, and you sort of kind of know that, oh, so the protons aren't the only thing moving in the experiment. There's also a bunch of voltage moving in the experiment. So it's like the cathode ray tubes, right? I mean, part of the argument was about the fact that they were a little bit unhealthy was it's not so much the electrons that were hitting the phosphorus and creating some radiation. It's just the fact that you're also sending all that electromagnetic radiation, the voltage, you know, the stuff that caused all that static on the screen. You're also exposing yourself to a lot of radiation in the form of radio waves, microwaves, you know, all kinds of different light that's also just coming right at you. That's what it is. It's photons. And, you know, that's another reason, you know, not to stick your face an inch away from a cathode ray tube. So yeah, so the argument that, you know, they have everything so precise that they know where they can account for all of this energy, and that somehow the energy, that the voltage that's moving the protons initially, well, it keeps them moving. I mean, the only thing the magnets are doing is keeping them from flying out of the device. So the magnets aren't giving the protons any momentum. The thing that's giving them momentum is the voltage. I'm sorry, yeah, I'm pausing for a second because I have to. Let me actually pause. I'll actually pause. All right, pausing didn't help me. I just don't remember whether how most of these things, these circular cyclotron kind of things work. Is there's a point where they have to do a voltage gap. They force the protons to accelerate through a voltage gap to get them going faster, and the magnets are just containing them in the circle, and the voltage gap is what's making them go faster and faster and faster and faster. And I think it's the same for the LHC, but I can't be sure. The magnets might be pushing them along like a motor. Might be the motor principle at work, but I'm not too sure. I'm not confident of which way it is. Regardless of which way it is, the point is that a lot of energy is going in to just moving these little protons, right? I mean, gigawatts of power are being used to accelerate them. And so clearly when this event takes place, the event isn't just about the proton having momentum. The protons bring with it a friend, okay, called the voltage. And the voltage is going to be doing something also. The lightning bolt the proton is flying on isn't irrelevant to the experiment. As irrelevant as as they've assumed. Let me put it that way. This looks like it's bigger for some reason. The camera did something while I was away. I don't know. Anyway, so yeah, we'll call this a video now. I think so. Yeah, it's enough. It's not one of my favorite subjects. Again, I don't really, you know, I have no horse in this race kind of thing with all of this extra bit particles. I'm just saying what's clear is that they don't have any lifespan at all. So even if we say magnets are made out of little homunculuses or something, and they, you know, what we clearly understand is that they don't like to be free homunculuses. They only like to be next to each holding hands. So it sort of doesn't matter to me if you can blow it apart into little pieces, but all the pieces just go right back into the form again. Okay, that's funny, it's interesting, but it doesn't really mean anything, right? Because I don't think you're ever going to make a quark gun or any one of these. You're never going to turn any of these little subatomic particles into a gun and shoot some, in my opinion, because they're really not elemental. They're pieces of energy. They're just little rays that we haven't identified correctly. Okay, it's like a broken X-ray. You know, it's still going to have a lot of energy in it, but it's broken. You know, it's not. They're little tiny rays instead of long enough rays to affect electrons the way traditional X-rays do. So they have a lot of energy in them, but you know, it's not going to behave like an X-ray. It's going to behave like a piece of force hitting it, like gravity. So we might be able to measure some of that, and then we'll call that a quark. But it's not really a quark. It's just X-rays that are broken. X-rays where part of the frequency has been pulled out of it. So it's only this much X-ray, then nothing, then this much X-ray, then nothing, then this much, you know. It's had some of its amplitude destroyed. Alright. And that's one explanation. I'm just saying, this is the kind of stuff where people could just do all kinds of speculating. You know, you could just speculate and speculate. Oh, does she have silicone in her ass? You know, you think she had a nose job? Do you think that she had her eyes, you know, turned straight? I mean, you could just sit here and play the game, but is there any point in playing that game? I don't think it's terribly relevant to the real game, which is really to understand gravity and magnetism. And I mean understand them in some kind of rational way where you just don't make up bent things and virtual things to explain anything. or like Ken Wheeler, you just make up counter space and hyperboloid and lack of magnitude and the jargon. I mean, his last video on black holes, it it was just the whole video was 20 minutes of just pure jargon. You can't make any sense of it at all. No mechanism, nothing coherent. No hammer, nail, not even close. It's simplex, but not simple. Phrases like that. One minute he says the big universe is just like the small universe, and the next minute he says black holes lose their reality. They're a non-reality. Where do I see that anywhere else? It's just bizarre. Anyway, it's just so depressing that most of the conversations are imbecile on imbecile. Just so bad. The imbeciles leading the imbeciles. It's just really depressing. Anyway, let's see if there's anything else to comment on, and then we'll be back in another half hour if I feel like it. Yeah. I am liking having the computers are actually working fairly well, so things are shaping up and such. Bugs still lots of bugs. My screensaver won't work if I have the camera open. No, I should point this. If I have the camera open, the screensaver doesn't work. That shouldn't that shouldn't matter. So anyway, little shit like that, just irritating. I never really bothered. Like I said, it's just because this new monitor I got for $50 is an LCD, and it's not good to have. They can burn in. So I found a fix in the sense that I made a little script, so I just hit it and the screensaver turns on. But I mean, I really don't want to have to turn it on. I mean, that's It is funny how computers have made us kind of lazy, and how your expectations for how things should work in the world is so different. With all this technology, it's like, oh no, it's too much trouble. I have to press this button. Watch this. I have to hit this button. Then I have to say run. Oh, that's just too much. I can't do that. I should do it. Well, no, I better not do it, just because who knows what images will pop up. Then I'll have to edit the video, and I don't want to do that. So anyway, I believe we finished our task here on the planet of the imbeciles. That's all you can say. Yeah, sorry. It's just, there's no point in calling humans anymore. We just ought to call them imbeciles, because that's all there is. They're just imbeciles. Idiots, imbeciles, stupid fucks, fucktards, whatever. I mean, we just come up with some kind of name that just points out that they're not evolving. We've devolved below the common sense of a minkie. The minkies have more common sense than people. Minkies wouldn't fall for hyperboloid bullshit. Counter space. What the fuck is that? Counter space. The unnothing. Antiparticles. Yeah, the minkies wouldn't fall for that. Come on. Alright, anyway, till the next time. And such.